Hello and welcome to my channel. Today I want to tackle example number 3 and the question is on the board. So the question reads, the figure below shows section of prestressed concrete beam. The beam is simply supported over a span of 10 meters and carries an imposed load of 30 kilonewton per meter spread over the entire span. The beam is reinforced with two wires, 40 millimeter from the top face and 10 millimeter wire, 60 millimeter from the bottom face, all spread eccentrically. All wires are 5 millimeter in diameter and the prestressing force is 1500 kilonewton. Determine stresses due to the prestressing force only and stresses due to prestressing force and imposed load at mid-span. Then the last question, illustrates suitably the resulting stresses at various stages. So the question carries 20 marks. This is the section. This is the section of the beam. As you can see at the top flange, we have two wires 5 millimeter in diameter, two wires 5 millimeter in diameter, and they are placed 40 millimeters from the top of this flange. Again, at the bottom, we have 10 5 millimeter diameter. So we have 10 wires 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 wires 5 millimeter diameter placed at 60 millimeter from the bottom. And then the bottom flange is 400 millimeter and the top flange is 200 millimeter. The web is 100 millimeter and the bottom width flange is 200 millimeter. The depth of the web is 600 millimeter and the width of the top flange is 100 millimeter. So let's see how we can tackle such a question. So solution. So when given such a question, don't waste any time. Start calculating the properties of this section. And property number 1 is the total area. Area total will be, so you will divide this section into various figures. So you will have number 1, number 2, and number 3. And then you will calculate the area for each one of them and get the total area. So we begin by the first portion, which is figure number 1. The area will be length times width, which is 200 times 100. So this is 200 times 100. Then plus, you come to this second portion, the area will be 600 times 100. So 600 times 100 plus the third portion, it will be 200 times 400. So this is 200 times 400. So area total is equal to, this is 200 times 100 plus 600 times 100 plus 200 times 400. So the area is 160,000 millimeter square. So this is the area of this section. We now proceed to the Y bar and Y bottom. So we proceed to Y bar top and Y bar bottom. So we can begin either from the top as we proceed to the bottom, or we can begin from the bottom as we proceed to the top. Whichever case you choose, the answers will be the same. So because there is not enough space, you will allow me to claim here, but we will use this information later, like the span, which is 10 meters, and an imposed load of 30 kilonewton. 2 wires 40 millimeters is already here. 10 wires 60 millimeters is already here. So no need for that. And then we will also use 1500 kilonewton later. So let me claim. So I want to start calculating a Y bar, and I will start from the top. So Y bar top. Y bar top. So we begin from the top of this section. So the area of this section, section number 1, will be 200 times 100, which is 20,000. So this is 20,000. This is 20,000. Times a half of this section, or this figure number 1, a half of the width of this figure number 1, which is 100 over 2. So you say 100 over 2 plus, we come to this number 2. Number 2 is 600 times 100, which is 60,000, times a half of 600. So this is 600 over 2, then plus, because we started from the top, so we will add 100. So plus 100, like that. And then plus, we'll come to the last portion, or the last figure. The area will be 200 times 400, which is 80,000. Then times a half of 200. So a half of 200 plus 600 plus 100. Like that. And then we will divide everything. So this is the larger bracket. You will divide everything by area total. So let's carry out the operation. So the answer is 89 times 10 to power of 6. Then you divide by area total, which is 160,000. So divide 160,000. So Y bar top is equal to 556. 556.25 millimeters. Now to get the Y bar bottom, you take the total depth. So that is 200 plus 600 plus 100. Then minus 556.25 5 millimeters. So this is 800, 900. So 900 minus answer. So you'll get y bar bottom to be 343.75 millimeters. So that is the y bar bottom. Then after calculating the y bar top and y bar bottom, we now proceed to the second moment area, which is Ixx. Again, allow me to clean here. But before we proceed to Ixx, let's indicate on our section the y top and y bottom together with its value. So as you can see in the figure, I have already indicated the y top, which is 556.25 millimeter, and the y bottom is 343.75 millimeter. So again, remember to write the total area. So area total is equal to 160,000 millimeter square. So I can comfortably clean here. Now to calculate the second moment of area, you will use this formula. So Ixx is equal to summation of BD cubed over 12 plus IgG. So I will start calculating the Ixx from the top of this section. So I will begin by the first portion. The first portion, it has B as 200 and D as 100. So this one will be 200 times 100 cubed over 12. Then plus IgG is the area of this portion, which is 200 times 100, that is 20,000. Then you multiply by, you will take the y bar top, which is 556.25, then minus a half of this width, a half of 100, which is 50. So this one is square. So in other words, IgG is equal to area times y bar top minus the y bar of the figure you are considering, and then you square like that. So area times y bar from the top minus y bar of this of the portion you are considering, and then square. Then plus, let's put our large bracket or our larger bracket. Then plus, we come to the second one, this one. So the second one, we have BD cubed, which is 100 times 600 cubed. So this is 100 times 600 cubed over 12. Then plus the area of this portion number 2 is 100 times 600, which is 60,000. This is 60,000 times the y bar top is 556, 556.25 minus a half of 600. A half of 600 is 300. Then plus 100, that one will be 400. This is 400 square. And then the last one, like that. Then plus, we come to this last part or last portion. So the BD cubed will be 400 times 200 cubed over 12. So this is 400 times 200 cubed over 12. Then plus the area of this portion is 400 times 200. So that is 80,000. So this is 80,000 times. This one is supposed to be like this. Then times the y bar top is 556, 556.25 minus a half of this 200 is 100. 100 plus 600, that is 700. 700 plus 100, that is 800. So 800, then square. So Ixx will be, now you carry out the operation to obtain Ixx. Punch your calculator to obtain Ixx. So Ixx is equal to 13.43 times 10 to the power of 9 millimeter to the power of 4. After that, we now proceed to section modulus, which is Z. So we have the Z top and Z bottom. So Z top will be Ixx over y bar top. So this one is equal to 13.43 times 10 to the power of 9 over y bar top, which is 556. 556.25. So this one is equal to, so divided by 556.25. So this one is equal to 24.14 times 10 to the power of 6 millimeter cube. Then you have the Z bottom. This one will be Ixx over y bar bottom. So this one will be 13.43 times 10 to the power of 9 over 343.75. So this one is equal to 13.43 times 10 to power of 9 divided by 343.75. So the answer is 39.07 millimeter cubic. Now, after calculating the IXX, Z bar top and Z bar bottom, what follows next is to locate the position of the prestressing force. As you can see in the section, we have not been shown the position of the prestressing force. So it is therefore needed to be calculated so that you can use the eccentricity to calculate the moment, the PE over Z. So we will calculate this position of the prestressing force, position of prestressing force. So let's locate this position from the bottom. Let's locate this position from the bottom. So locate position from the bottom. Locate the position from the bottom. So to locate the position from the bottom, you'll take the total number of cables, which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and assume they are being stretched from the bottom side. So you'll take 12 times Y bar bottom, which should equal to, now you come to these cables, we begin with the cable at the bottom part. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is equal to 10 times the distance from the bottom, because we are allocating the position from the bottom. So the distance from the bottom is 60 millimeters. So times 60. Then plus, we come to the top one, 1, 2. We have 2 times the distance from where the cable is to the bottom part of this section. So we are supposed to add this distance, which is 200 plus 600 plus 100, which is 900. Then minus 40 to get the distance from where the cable is to the bottom part. So minus 40. So this is 900 minus 40. So this is 12. Y bar bottom is equal to, let's carry out the operation for this. So we have 600 plus, this is 860 times 2. So this is 2320. 2320. Divide both sides by 12. So which imply Y bar bottom is equal to 193.33 millimeters. So we assume the prestressing force is at 193 0.33 from the bottom part of this beam section. So after calculating the position of this prestressing force, where the prestressing force is applied, you can now calculate the eccentricity. Yes, we can now calculate the eccentricity. So before I calculate the eccentricity, let's preserve this information, Z top and Z bottom, because we will use them in our proceeding calculation. So we have Z top, which is equal to 24.14 times 10 to the power of 6 millimeter cubic. And then we have Z bottom, which is equal to 39.07 millimeter to the power of 3, like that. So we now calculate the eccentricity. So for us to calculate the eccentricity, I will sketch the section again. This is the section. Is the same as this one. Like that. So we will assume this prestressing force is at this point. Let's assume it at this point, like that. So, and from the question, this prestressing force is, or this prestressing force you are given in the question, let me check. Is 1500 kilonewton. So this is 1500 kilonewton. So from the bottom, to where this prestressing force is 193.33. 193.33. And remember, the Y bottom is 343.75 millimeters. So this will be the eccentricity. This one is equal to eccentricity, because eccentricity will be the distance from the center of this section to where the load is acting. So E is equal to 343.75 minus 193.33. So this one is equal to 343.75 minus 193.33. So E is 150.42. Let's keep this information. So E is equal to 150.4342 millimeter. So I want to clean here. So we start now calculating the part A of the question, which says that stress due to pre-stressing force only. So stress due to pre-stressing force only. So part A, stress due to pre-stressing only. So we will begin by the direct stress, whereby P over A is equal to, our P is 1500 kilonewton, which is the pre-stressing force, times 10 to power of 3. Change it from kilonewton to newton. Then divided by area. Our total area is 160,000. So this one is equal to 1500 times 10 to power of 3 divided by 160. 160,000. So this is 9.38 Newton per millimeter square. And then again we'll calculate PE over Z. So for this, we will have PE top and PE over Z. So we'll have PE over Z top and PE over Z bottom. So we begin by PE top. Sorry. So we begin by PE Z top, which is equal to, our P is 1500 times 10 to power of 3, and our eccentricity is here 150.42 over Z top. Z top is here 24.14 times 10 to power of 6. So this one will be, so the answer is equal to 9.35 Newton per millimeter square. We proceed to PE over Z bottom. So this one will be 1500 times 10 to power of 3 times eccentricity, which is 150.42, all over Z bottom 39.07 times 10 to power of 6. This one should be times 10 to power of 6 millimeter cubic. So the other is equal to 39.07. So the answer is equal to 5.78 Newton per millimeter square. So that is part 1 of the question. We now proceed to part 2 of the question. So allow me to clean here. So let me write here let me preserve this information. P over A is equal to 9.38 Newton per millimeter square. Then PE over Z top is equal to 9.35 Newton per millimeter square. And then PE over Z bottom is equal to 5.78 Newton per millimeter square. We now proceed to stress due to imposed load. So Roman number 2, it says that stress due to pre-stressing force and imposed load at midspan. And imposed load at midspan. So it means we will not calculate the on weight of the beam. So do not calculate on weight of the beam. So we'll use the imposed load to calculate the moment. And the imposed load is equal to 30 kilonewton per meter. So this is 30 kilonewton per meter. So if this is the beam, this will be the imposed load, which is 30 kilonewton per meter, and the length of the beam is 10 meters. The length is 10 meters. So M max is equal to WL square over 8. So this one is equal to 30 times L, this is 10 square over 8. So this one will be 30 times 10 square all over 8. So this is 375 kilonewton meter. And then from there you calculate the stresses due to imposed load. So stresses due to imposed load. So we will begin by the top side. So this is M over Z top. So this one is equal to 375 times 10 to the power of 6. So we are converting from kilonewton meter to Newton millimeter, and the Z top is here, which is 24.14 times 10 to the power of 6. So this one will be 375 divided by 24.14. So this is 15.53 Newton per millimeter square. And then we have M. We have M over Z bottom. So this one is equal to M is 375 times 10 to the power of 6 over Z bottom, 39.07 times 10 to the power of 6. So this one is equal to, this is 375 divided by 39.07. So this is 9. This is 0.60 Newton per millimeter square. Then after that, we now combine all the stresses. We now combine all the stresses. So the combining will be as follows, or the combination. So combination now combination. So we'll do the combination for the top fiber. So for the top fiber, we'll begin by P over A minus P E over Z top plus M over Z top. So this one is equal to PA is 9.38 minus PE over Z top is 9.35 plus M over Z top is 15.33. 15.33. So this one is equal to 9.38 minus 9.35 plus 15.33. This one is equal to 15.36 Newton per millimeter square. And then you come to the bottom. So the bottom fiber. So bottom fiber will be P over A plus P E over Z bottom plus M over Z bottom. So this one is equal to 9.38. This one remains the same. 9.38 plus the bottom one is 5.78, then minus 9.60. So this one will give us 5.36 Newton per millimeter square. Then the last part of the question is to illustrate. Illustration. So for the illustration, we begin with the direct stress, which is P over M. So this is P over A. So plus, remember at the top is 9.38 plus, we are done with these two. So the top is negative 9. So remember, on the left side of this line is negative and on the right side is positive. So 9.35 it will be here. This is 9.35 and then 5.78. 5.78, and then you join the two like that. So this is plus. Again plus. We come to this 15. At the top we have 15. This is positive. So this is 15. 9.33, and then the bottom is 9.68. 9.68, and then we join the 2 like that, is equal to now we have 15.36, which is positive. This is 15.36, and 5, again positive, 5.3, 5.36, and then you join the 2. So this is positive, negative, negative, positive, positive, and this is P E over Z, M over Z, and then the resultant. And the question ends there. So thank you for your time, and we meet again in my next session. For those who have not subscribed to the channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video.